a hockey puck has a mass equal to, what are hockey pucks? They're kind of dense, maybe 0.8 kilograms. Right? The hockey puck has a mass of 0.8 kilograms, and the hockey player is going to, it's on the ice, and he's skating up to it, and he's going to take a slap shot or a whatever shot, and I'm again cheating, and the puck is going to move off towards the goalie at 56 meters per second, and the stick is in contact with the puck through a distance because it's moving along the ice, all in contact, let's say 20 centimeters, so 0.2 centimeters. So the question is, how much work is done on the puck by the stick, and what's the force that the stick exerts? So those will be our two questions. So how much work and what is the force? And that will get us practicing two equations in this one too. All right, so the work energy, we have to solve this with work energy. So the work energy theorem tells us that the change in kinetic energy equals the net work acting on the object, the net work, and that is key. It is the net work. So we gotta look at all the forces. This is where that free body diagram comes into play. So the change in kinetic energy, of course, is the final kinetic energy minus the initial kinetic energy. So that equals our net work. So how do we determine the net work? Well, we have to identify the object. The object is the hockey puck. So what forces are acting on the hockey puck? Well, we have the force of gravity between the puck and the earth. We have the normal force between the puck and the ice. And then we have the force of the stick between the puck and the stick. And we will assume frictionless, but if we didn't assume frictionless, we'd have to add that one in too. All right, so there's our free body diagram. When we do that, we then identify that any one of these three forces could be doing work. And we know that work is the force times the distance in the direction of that force. So the force parallel to the distance. Now, work one is the force of gravity. It's the distance is in the horizontal direction. We think of that ice on the, puck on the ice. And so the force of gravity doesn't have a component in the horizontal direction, so it can do no work. If the work is not, if the force, excuse me, is not in the direction or doesn't have a component in the direction, and we don't do any forces with angles, so for your purposes, just in the direction, then it does no work. So anytime a force is not in the direction of the displacement, it does no work. Force number two is in the direction. We don't know that force. We'll call it, I'm getting to you, Mullen, wait. Yes, then green. Okay, green is bad. Thank you. All right, so we don't know the force of the stick, but we do know that the work is, or that it covers at 0.2 centimeters. And work number three is the normal force times the distance But again, this is not in a parallel direction. So the force for the normal force is also 0. So the normal force is 0 here because the force is in a direction that is not in the same direction as the displacement. It's perpendicular. So the only force acting is the force by the stick. So the question says how much work, I didn't finish the question here, was by the stick, right? And by doing the free body diagram analysis and the work analysis, at this point we can say, well, the only work done is by the stick, which means that the net work is equal to the work done by the stick. So I can look at the change in kinetic energy. We are told that the final speed is given, and I said that the initial speed, it was just sitting there. So we have 1/2 0.8 times 56 squared. If the initial speed is 0, it's just sitting there, and I'm using speed properly. Remember, energy is speed, not velocity. That equals the work done by the stick. So, my calculator, we have 0.5 times 8.8 times 56 squared. To get the work done is 1,254 joules of work by the stick. The second problem asks, well, how big is that force? And now we can utilize the work we've already done. So we know that the work done by the stick is equal to the force by the stick times the displacement. So I have 1,254 is equal to the force of the stick times 0.2. So divide that by 0.2 and we get 6,272 newtons is equal to the force by the stick. All right, so that lets us practice the work and the work energy theorem. And let's just say if the stick is in contact with the puck for, let's just round out this unit for, I don't know, 0.5 seconds, how much power is exerted? Our power is equal to our work per time. Our work is equal to 1254, our time 0.5. Oops, let's turn around, calculator off. So we have 1254 times 0.5. No, times 0.5. 1254 divided by 0.5, so times 2. Our power is 2508 watts. So we got power in there also. All right. So questions on any